Tēnā koutou, tēnā koutou, tēnā koutou katoa. Ko Tania Williams tōku ingoa. Good evening. Thank you all for joining us both in person. I'm thrilled that so many have come out in these COVID times, and also to those of you who are online. We're thrilled that you could join us this evening. I'm one of the general managers at Engineering New Zealand, and we are so thrilled that this is finally going ahead. Talking to Robin just before the conference, the Australasian Engineering Heritage Conference was due to go ahead in November 2020, then November 2021, and now we've decided to change the format, and we are having a series of events held in different regions, which you can join. So here in Wellington tonight, but if you look at our website, you'll find where the other ones are, and we'd really encourage you to go online and hear the wonderful presentations that people have put together. We'd hate you to miss out just because COVID meant that we couldn't have a conference. So please do look online and join us for some of those other sessions as well. So our first presenter, and you might have caught a glower, Chessa Stevens is a principal conservation architect and National Building Heritage Lead at WSP. In her role, she specialises in assessment, preservation, restoration, management and maintenance, planning for heritage and historic structures. Chessa will now share the story of two bridges.
Kia ora koutou katoa. So I've just had an introduction. I'm Chessa. I won't bore you with the longer details of my various different roles and qualifications today. I'm here to tell you about two bridges, the Rakaia Gorge #1 bridge and the Opawa bridge, which you've just heard a little bit about. The paper essentially discusses, from my perspective as a conservation architect, the two different approaches that were taken with these two bridges in terms of balancing engineering constraints and requirements with heritage significance and value, and arriving at a solution that was a compromise for everybody in both cases, but was worked through by engaging with each other and preparing a conservation management plan. So firstly, the Rakaia Gorge #1 bridge, which is in inland Canterbury. So for those of you who don't know inland from Rakaia, not the Rakaia bridge, which is down towards the coast. This was constructed in 1882 under the supervision of the Public Works Department, and it was initially intended to carry both road and rail, but it is one lane. Its unique design has historically led some to believe that it was conceived overseas, most likely in the United States, where experiments in bridge design and engineering at the time had led to the development of several new types of arch structure. However, we are fairly confident from the information that we've been able to gather and establish over the course of doing the historic research that was undertaken for this project, that it was 100% true blue Kiwi designed, although the relevant engineers who were involved had had some experience in the United States. The design draws particularly on the works of Wendell Bowman and Albert Fink, both of whom worked on the groundbreaking Baltimore and Ohio railways. But as I say, we're pretty confident that the Public Works Department were 100% behind the design of this particular structure, which is unique in the world. It differs from the Bowman and Fink trusses in that the diagonal ties are anchored at each end within concrete-filled sockets and are tunneled into the rocky outcrops of the abutments. The girders are supported completely independently on cast iron pedestals, and they do not act as a compression cord. So strictly speaking, the bridge isn't actually a truss at all, but it does get referred to as being a truss. The initial design was a little bit deficient in terms of dealing with the weather. The Rakaia Gorge at this particular point is very narrow, and there are multitudes of Māori legend that precede the construction of that bridge that will tell you about the excessive amount of wind that occurs in this location. In 1889, some severe damage was caused to the bridge, and so the Public Works Department determined that some additional bracing was going to be required. Now, following that, there were multiple different disputes between two local councils as to who really was going to be responsible for upkeeping and maintaining this bridge. It's right on the border between two local authorities, and it still is. Essentially, it received very little maintenance until it became part of a state highway and under the management of the New Zealand Transport Agency. The effects of the harsh environmental conditions and a considerable increase in the weight and number of vehicles that were crossing the bridge have exacerbated problems caused by deferred maintenance over time. So when I became involved with this project, WSP, who I work for, formerly Opus, had been monitoring the condition of the Rokai Gorge No. 1 bridge for many years as the Transport Agency's structures management consultant. In 2016, a number of the transoms of the bridge had already been strengthened, and the loading capacity of the bridge had been limited, as had the speed. So we were talking about there was a mass you couldn't be over if you were going to be driving across the bridge, and you had to go over it really, really slowly. The carriageway is restricted to 3.5 metres. That's allowing for a very narrow border either side. And this was causing quite a lot of issues for the Transport Agency as this route was becoming more and more popular, but it also is quite an essential rural route. And we've got things like stock trucks, logging trucks, milk tankers that need to use this route. And it is the secondary emergency access. So if the Rokai Gorge Bridge is, for whatever reason, out of action, this route is the only alternative route that there is on this side of the Southern Alps. Timber drilling investigations were indicating that about 75 millimetres down into the timber decking, there was deterioration, and there was ongoing. So we've been doing this, had been happening for a number of years, and it wasn't getting any better. So it was at the point where the engineers felt that it was no longer practical or sufficient to remediate the decay. The level of decay plus load meant it really needed to be replaced. Further to that, the instability of the surrounding rock outcrop, the potential unseating of the girders from their pedestals, unclear longitudinal restraint system, and failure of bracing meant that the bridge was also seismically vulnerable, which of course became much more of an issue after the Canterbury earthquakes. Consequently, it was concluded that the truss should be strengthened and that the bridge deck should be replaced. Replacement of the deck would require the timber balustrades to be removed, at least temporarily, and given their poor condition and their non-compliance with current bridge safety standards, it was assumed that these balustrades would be replaced. Design for strengthening and deck replacement was commenced by WSP Bridge engineers in 2016. And as the documentation was being completed, the design team approached our archaeologists, because the structure is a pre-1900 and any work that gets done to it, it requires an archaeological authority. The archaeologists' heckles went up and they said, this is a listed Category 1 structure with Heritage New Zealand. It's scheduled with the council. Have you consulted a built heritage expert? And the engineers said, what are you talking about? At which time they came and saw me. So the proposal at that time was to remove the entire deck, including the balustrades above and the transoms below. So effectively everything was coming off the truss. Above the girders, we were replacing it. The new transoms were going to be steel. The deck was going to be a new deck system, which is a compound plywood decking system. And the balustrades were going to be metal with new crash rails, completely different design. So recognising the heritage status of the bridge and that engagement with Heritage New Zealand was also going to be necessary, it became fairly apparent to me pretty quickly that the proposal wasn't going to be acceptable. So we got around the table with the Transport Agency, the engineers, myself and Heritage New Zealand, and we looked at what we could do about this. And essentially what happened was we went right back to the start. So I said, what do you know and understand about the values of the structure? Oh, it's got a really important truss. Yep. What else? Nothing else. Okay. Not true. So that was the point at which it was agreed that we would carry out a conservation management plan. So a conservation management plan essentially will identify the significance of a structure and its various parts, and then will provide a set of policies for managing that structure that ensure that the heritage values of the structure are maintained and preserved, and it is intended to guide the future management of a place. So once we agreed that, we prepared the conservation management plan, we got back around the table and said, now that we've got this information, how can we use this to inform the design? And essentially what that did was force the engineers to go back to the drawing board and start again, which sounds expensive, and it was, and sounds like it would have caused time delays, and it did. But the result was a much, much, much better one. So the original hardwood transoms, which were a highly visible element of the design when viewed from the underside of the bridge or viewed from the roads approaching the bridge, were past the point of being able to be retained when it was considered alongside, when the level of decay was considered alongside their weight. So we did end up taking everything down to the girders off the bridge. The engineer's original proposal was to replace the timbers with steel transoms at much wider spacing, so alleviate the weight on the truss. And the intention was simply to discard all of the timber. So in the end, our compromise solution was to salvage all of the timber and splice timbers onto the ends of each of the new steels, and then intermittently space out timber false ends between them to replicate the original appearance of the structure. The mass concrete parapets at each end of the bridge were also in very poor condition, with widespread cracking and a lot of microbiological growth. So where you get cracking and you've got moisture, you get moss, you get lichen, you get things growing in there, makes the cracking worse. The engineer's proposal was to inject a high strength mortar into these cracks. However, this concrete is from the 1880s. It's very soft. If you inject a high strength mortar into that, you're going to create problems in the future. The soft concrete will start to fail around the really, really high strength injection. So we had to look for ways that we could carry out repair of this concrete without creating further problems down the line. And we used specialized concrete products. That's still cementitious, it wasn't lime-based, following a comprehensive analysis. So we took samples, the samples went overseas, they were analysed, they came back, we got information about exactly what the mix was, and we were able to specify the right kind of product to suit that would be completely compatible with the historic concrete. The whole, every parapet had its render removed, but we had areas of historic graffiti that I didn't want them to take off. Some of that graffiti is dated. We had dates 1920s, 1930s. So those areas were cut around and retained. And then when the new render went on, they remain in place. Everything's been now repainted in an appropriately compatible paint. And they've also received a biocide application to prevent, well, to inhibit the growth of future vegetation. So again, a good result. Part of the conservation management plan was an analysis of the existing balustrades to determine how many of the members had been replaced over time. It was very obvious that there had been replacement, but we didn't know the extent of that. So this analysis that I undertook then informed the decisions that we made about what members of the balustrade were retained and what could be discarded. We searched for an appropriate hardwood to replace what we had. We couldn't find the exact timber. We ended up importing one from the States to replace it, and we engaged carpenters to form the members and join them in exactly the way that they had been originally. So we took each section of the balustrade apart, conserved the original members, and put them back in their exact positions after they'd been labelled and numbered, and then intermittently, as required, and there was more than we had initially expected, replaced the members that were removed with these new ones, all following the same design, all jointed in exactly the same way. We did use new fixings in some cases because the existing ones were no longer in the condition that they could be reused, but also we do have health and safety requirements and engineering requirements that had to be met. But we did also conserve all of those, and we did put them back on where we could. So essentially, the longitudinal timber decking, which all came up, we didn't have a use for that because the new decking system, which was a plywood system, was going to go down, and that was one of the compromises that we'd made whilst we were working through all of the options for the bridge. The weight was too much and the level of decay was quite significant. So we looked at some other options for how we could use that timber around the site, and we were very fortunate that a neighbouring property, they've just created a walking track through their property very close to the bridge, and they took on some of those timbers and used them for furniture and to create some signage. So we tried very hard to make sure that everything that came off the bridge was reused if it could be, and of course it was all also recorded as part of the Archaeological Authority. So balancing heritage, engineering and safety performance requirements at this bridge did not come without compromise. It was not possible to avoid all negative effects on the bridge's heritage values, nor was it possible to achieve a design that was compliant with the Transport Agency standards for new bridges. This balustrade will never meet those requirements. So we all had to compromise. However, it was the understanding of the significance of the bridge and its fabric and the appropriate levels of intervention that were based on this significance. This was critical to understanding how we could make a compromise that achieved the engineering outcome that was needed whilst not destroying unnecessarily the heritage values of the structure. And this was recognised with a CSOC Heritage Award in 2021. So now the one you've all been waiting for, the Banana Bridge, or the Opawa Bridge, which was commissioned in 1914, constructed between 1915 and 1917, keeping in mind that's World War I. And this bridge replaced an earlier bridge over the same river at Grove Road in Blenheim that had been washed away 40 years before. So between that earlier bridge and this one, people crossed using the railway bridge, which is a little bit further downstream. There was no road bridge here for 40 years. This one was also designed by the Public Works Department, but we know that that was chaired at this point in time. This design was championed by J.D. Holmes, who was under the supervision of his father, R.W. Holmes, and who was the engineer-in-chief at the Public Works Department at that time. The structure comprises 8 reinforced concrete bowstring arch trusses. So they're not bowstring arches, strictly speaking, because those would just have vertical members. They are trusses, but they are also bowstrings. So again, another fairly internationally unique structure that was used here. They're an adaptation of a Pratt truss with crossed members at the centre and a top chord that forms a true arc. So loads on the bridge deck are carried up the hangers to the top chord of each truss, and the trusses are tied at the base with a bottom chord that prevents them splaying all over the place effectively. The joints at the end of each truss, one is fixed and one is on bearers, so it moves. And these photos, just as a quick aside, we were very fortunate to obtain these photos from the daughter of a man who was involved in constructing the bridge. These are from the site, and you can see the volume of reinforcing steel that was used in the construction, that there is no shortage of steel here. So as I said, generally each span is simply supported. It's fixed to reinforced concrete pier at one end, it rests on steel bearings on the other. This created slip joints on the bridge. It allows it to move. But unfortunately, what's happened over time, as you might expect, is that the road's been resealed and resealed and resealed, and those joints in the deck were all covered up. So we could see the cracks where those joints were, but they just get covered over every time. Like the Rokai Gorge Bridge, this is a pretty striking example of our New Zealand-based engineering innovation at the time. It's an amazing structure, but also an example of how deferred maintenance or inappropriate maintenance causes problems. Not the least of which, as has been noted, it was rather narrow, which wasn't a problem when it was built, but became a problem quite quickly, especially when it became part of State Highway 1. So as you've heard, and as I can describe from my own experiences, if you were oncoming towards a large truck, a bus, something of that nature, you definitely felt like you didn't have a lot of room to go anywhere. And you could see the damage on the bridge that had occurred as a result of this. The scrape marks all along both sides on the trusses. There were little bits of fragmented metal and truck and things just on the ground, sort of as a routine. So there definitely was an issue. That the Transport Agency, in its former machinations, had in the 1980s actually looked at this. It was the Ministry of Works at the time, had looked at this. They knew it was an issue right back then. Then they decided it was a bit too hard, so they didn't do anything about it. And so actually it came to 1990s, we're still doing nothing about it. 2004, they installed some seismic linkages to help prevent the spans from slipping off their bearings. There'd been a bit of ground shaking, they were a bit concerned, but essentially the ongoing issues around the potential for this bridge to be seismically vulnerable was what triggered eventually the replacement. So funding was raised over many, many years. In the meantime, nothing was done on the existing bridge. The situation was getting worse. We also had quite a large amount of scour happening on a couple of the piers, so they were being undermined from underneath. And generally speaking, by the time we got to the bridge, it wasn't in a particularly good way. So when we came to the point where a new bridge had been designed, it was commissioned, we knew it was happening. Attention was turned to what do we do about the existing bridge. So while the design process was occurring for the new bridge, we got in early. We sat down with the Transport Agency and the engineers and Heritage New Zealand, and we said, this is a really significant heritage listed structure. What's your plan? Well, what are we doing here? And the Transport Agency had never intended to demolish the bridge. They always wanted to retain it, but part of that retention was in the future the idea of handing it over to the local council because it would become pedestrian and cycleway. It's decommissioned from the state highway. It's no longer something that they want to be responsible for. But fortunately, by getting in early, we got a conservation plan for this bridge underway right at the early stages of the project. So that was happening in parallel with the design of the new bridge. And that meant that as that was being formed into specifications and drawings, we were also saying we've got specifications and drawing things we need to do to this existing structure to ensure that not only that it performs well as a pedestrian and cycleway, but to make sure that it is given some much overdue maintenance and that's done in the appropriate way, and that it's in the best possible condition that it can be in if and when the Transport Agency look to hand it over to the council, because the council's not going to want to inherit an asset that's got many years of deferred maintenance, including potentially seismic strengthening issues and scouring issues. So on top of all of that, we had a few of the very typical things that you see in a concrete structure that's got a lot of reinforcing that might not have some particularly good concrete cover on it. Rusting of the steel underneath, forcing the concrete to spool, had some cracking, We had some just general deterioration of the render, and we also had quite a lot, as I mentioned, of mechanical damage. So what we didn't want to do with this project was try to make the bridge look new, because everything about its existing form, including the scrapes and the marks and this, they all tell the story of the bridge. Those things are significant, but we did need to address the bigger deterioration issues, and we also needed to address the strength. So we made some, first of all, we removed all of the appendages that were on the bridge. So this bridge was the key connection from one side of the other. All of the telecoms, all of the power cables, everything was attached to the side of the bridge. They all got integrated into the new bridge design, which was really essential to being able to restore this bridge. So once they'd moved, everything was off there, it was de-trafficked. We had a clear run to do a really good job of restoration. And the first thing after that, the first thing that we did was we gave it clean. Now, it's never been cleaned in its life. And we were testing a method of cleaning. It's really, 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 really high temperature steam cleaning. Hadn't been tried on a structure of this kind before, and we weren't sure what the results were going to be. Fortunately, they were really good. But what it also did, and we knew that it was going to do this, and it was part of the plan, was that it would start to reveal in greater detail where we had more deterioration. So we brought specialist operators down from Auckland to use the Thermatec cleaning system, and I would highly recommend it for many kinds of historic structures. It's an excellent system. It's imported from the UK, and it does need specialised operators to use it, but you can see there how much of a difference that made. Then we did a whole lot of other little things that all made a big difference. We cleared out the drainage ports. They were all blocked. We removed all of the layers of seal that were on the bridge joints, cleared them out, put little steel brackets on the end of each one. Now they're open, the bridge can move. No more cracking. We made repairs to the concrete. So we did identify on the basis of how bad the deterioration was, spalling and cracking, whether we had visible signs of rust coming through the concrete, those kinds of things, to put it in layman's terms. We had a run sheet. This is the level, the worst level through to the best level. This is how we're going to attack it. And we used specialized products that were compatible with the concrete of the bridge, took the concrete round the corroded areas off, treated that, reinstated. We had some previous paint coatings and other things in different patches of the bridge that were cleaned off. And all in all, what we got left with was, sure, a structure that actually still looks pretty raw, but it looks like it's 100 years old, which it is. And it still tells its story, but it does it in a way that's also not deteriorating at the same time. We applied, and again, a biocide treatment to it because it was quite prone to developing microbiological growth. One of the most challenging aspects of the project was how to integrate lighting and power supply. So we wanted this bridge to be able to be used as a venue for markets or stalls. So we needed to be able to supply those stalls with power, and they also needed to be able to fix their structures to something. Because if you're going to bring a tent on or a marquee onto the bridge, what we don't want you doing is trying to fix it into the truss, because that will cause damage. So we fitted the deck out with hooks, flush, obviously, so that you can cycle over them, no problem, but you can tie your structures down to them. And we've got trunking along one side of the bridge that provided the cabling for all of the lighting and the power that's going to be used by people who will be using the bridge for that sort of thing. The facade the illumination of the bridge facades was an interesting conversation. Personally, I would have gone for warm white. Transport agency were quite keen on lots of colours, so we went for lots of colours. I'm told they can be warm white. I'm not sure warm white has been chosen yet, but that's okay. We actually used modified facade luminaires to ensure that the lighting that was going to be lit up towards the bridge, it stands out from the bridge, it's fixed around the balustrading, it doesn't fix to anything of the structure directly. And we had quite a long difficult process of finding the right design to make that work. And in terms of the result not damaging the bridge, it was a really, really good outcome. So what I can't wait to do is actually see a big community event on it, which I don't think we've had the chance for yet because of COVID and whatnot. So it would be really, really great to see something like that happen. The approaches to the bridge, the timber railings were reconstructed to their original details and restored. The significant pau whenua was commissioned as part of the project, and it is the northern gateway to Blenheim now. You know you're coming into Blenheim. The courtyard that's at the northern end of the bridge has interpretation panels, and those were informed partly by the conservation plan and also partly by the engagement with the three mana whenua parties that were a massive part of this project. And one of the piles from the earlier bridge, the 40 years ago bridge, was excavated in the course of this project and is also now in that interpretation area with a plaque. So we managed to bring all these threads together as part of the bridge project, which was really, really cool. And essentially what this really demonstrates is how starting with a conservation management plan will get you to a better result. So both of these bridges that I've talked about today, they had different issues. They came to the table with different problems and we worked through different solutions. But essentially what everybody could take away from the different experiences that we had with this bridge was how valuable it was to have a built heritage specialist engaged at the outset and a really good conservation management plan prepared before you start making interventions. And we've been very lucky that both projects were recognised with awards, and they really demonstrate not only our current abilities to work through solutions and compromises with the right people involved, but they also really celebrate a really long and very important history that we have in New Zealand of some unique engineering. So I hope you've enjoyed the presentation.
Thank you, Chessa. That was a really fascinating presentation and very close to my heart, as you hear. I'm just going to move right along to our second presentation. So next up we have John Finnegan. Seismic engineering and innovation are a passion for John. He's a technical director of over 35 years of international structural experience, currently at Auditorium. John is going to share with us some insights into the seismic strengthening and refurbishment of a Category 1 building, the Dunedin Law Courts.
Thank you very much. Tēnā koutou katoa, everybody. Greetings and good evening. I'm John Finnegan from Auditorium, a technical director there. Now, this is quite an old presentation now. We finished the job quite a while ago and it had quite a lot of relevance for the Dunedin seminar. So some of you might have seen some of these clips before, but it is a very fascinating story. So there's the original building. You can see it very similar to today. And I don't know if this mouse is working, but you can still see the horses, the trams, the dress that people are wearing. Quite an amazing sort of a building and really one of our fine buildings. If you know Dunedin, there's the railway station nearby. So it's quite an impressive structure, especially for the time and well before our thoughts of seismic engineering, that's for sure. And that gives you a little bit of an understanding of the decor of the building. We have Oamaru stone, the limestone. We have brick here, and we have some beautiful cast iron, as you can see in the colours there. So some of the features of the building, 1902. It is really a massive building. It's unreinforced masonry. So typically the external walls were cavity walls, brick here in Oamaru, limestone, a big cavity, and an internal brick on the inside, mainly 2 stories, 4-story tower. And we had all sorts of weird tunnels and undercrofts. There's the old jail from next door that they still bring the prisoners in from underneath and they pop up in the middle of the High Court. It's all quite magical. All of the floors are all timber. And I say here recently replaced for the timber roof truss. It was mainly a lot of the timber was retained, but certainly the sheeting on the top was replaced. There's some very large limestone ornaments hanging on the outside. And the foundation is a funny old mixture, especially for a modern engineer, of sort of unreinforced concrete strips, concrete pads, brick piers. It's quite a mixture, really. We were very, very lucky to be able to retrieve the original drawings, and these were absolute gems. And we were able to recreate these in very fine detail in 3D Revit. And they formed the background very much of how we were to approach the building. In fact, the architects, Stevens and Turner, took our drawings from the details that we had, and we drew every joist and bear on the job with this. Spent a long time getting there with that, but it was really valuable in the long run. And you can see pretty much the tower is the major feature, but there's all sorts of complexity in there, and that brings us to the foundations there. We didn't do laser scans at all, but we did do some measurements, and we found pretty accurately that the original builder had built that pretty much in line with the documents that we had. So it was a wonderful start having that turned into 3D. Some of the requirements for the project, now Ministry of Justice, the client, they were going through their buildings throughout New Zealand. They were looking for pretty much a 67% MBS level for all of their buildings. This was the same for this building. They needed a 67% for this one. Being a Category 1 heritage building, that brought it into an importance level. The issues that we had to think about: unreinforced masonry, it was earthquake prone. In fact, it was quite interesting when we first went there, because it was still inhabited only at the very ends, because they were very concerned about the tower, and so there was no one working in the full zone of the tower, but they were using the library and some offices at the very far end. So they were very conscious of the time. It was still in use, but they were not actually anywhere near where the tower might potentially fall. The ground, not wonderful, funny old reclamations from those times. You'd imagine a reclamation in 1902 wasn't too sophisticated. And we had some asbestos in the roof. And one of the major points was that the internal was just fantastic, beautiful timber and wonderfully crafted. I haven't written down there that the externals also had to stay pretty much pristine. We had no allowance at all to adjust the external of the building. So for engineers out there, which most of us are engineers, the Category 1 brought that as a building of culturally importance, culturally sensitive, and deeming it to be importance level 3, 50-year design life, 70%, as I mentioned before. Subsoil was pretty rough. It's very unusual soils there, and a lot of the ground was been built on over the years particularly poorly, and luckily a fairly low Z factor. So I think this is pretty common for a lot of engineers who have been dealing with existing buildings. You establish what you've got there. So we took cores out of the walls, out of the timber. We created the model, which we spent a long time doing, but that really made a big difference. Understood what was actually supporting the building, what was the foundation, understanding how do our diaphragms work, because it's about connectivity, joining floors together, floors to walls, the detailing of that. So it's a global look and also a detailed look. The tower is it's quite high, about 25 meters, and extremely heavy. It was very, very thick masonry, and someone had a bit of a crack of strengthening it before. I'll show you some pictures. It was a pretty miserable job, if I may say so. There's all sorts of elements there throughout the building they had to take care of. Big thing for masonry building is what's its strength, in line and out of line, out of plane. And we have typically throughout the building 2 leaves for the waterproofing. So that was another element, tying those masonry walls together. The courtroom floor, lots of complaints about how that performed, and the unusual ornaments on the outside of the building, which we'll see. So the first part of it was to understand what was the makeup, what was the mortar like, what was the materials like, what was the quality like, understanding foundations. It was a bit of an unusual scenario with the ground floor, in that apparently all of the cabling and heating pipes had asbestos. And what they'd done is they'd somehow knocked the asbestos off onto the ground below and covered it with concrete. So the access to foundations was really challenging, because whatever clever person had decided the asbestos, they buried it into the building. So it made it really, really challenging to come up with a system that tied foundations together without digging up all the old asbestos. So that was one of our issues. The masonry itself, you can see the core there, it's looking pretty good. Some of the other parts of the building, that's the brick piers for the internal timber. Some of that was pretty ratty. That's the northern face of the building. That's the tower. As I say, it was big and monstrous. And that's one of the clips from the drawings that we were doing, all broken down into sections. And we spent a lot of time actually recreating that. And it really did make a big difference as to understanding engineering design, architectural impact. It was a big part of our strategy. The tower itself, again, we carefully model that, and you can see we even modeled the Tourells on top of that as well. Now, just to give you an understanding of how it is actually a very, very big building. A lot of people would have seen the building. Very high floor to floors, 4 to 5 meters, and the tower poking up another couple of stories above that. And you can see also from the foundations there, traveling from one side to the other side of the building, and the original builder cut himself steps to find the good ground where they could bear on. So that was another challenge. Some of the undercrofts were very, very small, and some of them were extremely tall. So that was a challenge in itself. And again, the disparity, engineers like diaphragms, and all diaphragms lined up. So this diaphragm didn't line up at all particularly well. So we had to take that into account as we looked at all this and effectively use the walls and the locations that we had. So the engineering is about connectivity, and most engineers will know those walls need support at levels, the diaphragms need to work, the connection details, and there's lots of funny connection details. They all need to work both globally, but also individually. And just another shot of the cross section. So some of the strategies, so the foundation, you remember the drawing from before. So we overlaid the very bottom above the concrete blinding, which was above the asbestos, with a 200 concrete slab effectively. You can see that in green. And that unfortunately had to punch through all of the load-bearing walls and piers to tie that together. So the poor old builder, Amalgamated Builders, he couldn't believe what he had to do when he won the contract. He sort of misunderstood the requirements of this concrete slab. He was just putting a concrete slab on the bottom there, but he actually had to tie together all of the external walls, the internal walls, and so he had to drill through all of those, grout them back up, and then pour reinforced concrete at all sorts of different levels. So it was a pretty miserable job for the guy. They did a fantastic job. You know, they hung in there, the local builder, Amalgamated Builders, and they took it seriously, and they did really, really well. So that was the key part for the bottom. We held all those foundations together. You can see the bits in green. What's coming up? Are you seeing that? Possibly not. Yes. The bit in the red in the middle that's a big, hello, we've jumped forward. So that's the actual, we had to recreate the foundations for the tower. There was, so the bearing pressure was very, very low, and the combination of a potential for liquefaction and a very low bearing pressure meant that the weight of the tower, and especially when we put some extra sort of structure into there, meant that we really had overloaded the foundation capacity. So that was its own special little example itself. And we had to increase the bearing of the ground, jet grouting. And we also had a big raft down there, all put in an existing building. So it was impossibly challenging for the builder to do, but he got there. Other parts of the building just had some suspended concrete slabs. The next one, and the ground floor diaphragm was hugely complicated. Initially, we'd thought, how do we retain both of the timber floor? And we schemed a diaphragm that ran on the underside of all the bearers and joists to hold it together. And that way we could keep skirting boards, door frames, all the sort of architectural treatment, because I've got a picture at the end which shows you how beautiful the inside of the building is. And in the end, the builder said, look, we'll just have to rebuild all of that. We'll put our diaphragm on the top. The actual putting a diaphragm underneath all of that sort of timber is just too difficult. What we'll do is we'll safely store all the timber floorboards, tongue and groove floorboards, put it away, number it, look after it, and bring it back again in the right place. So to their credit, that's what they did and brought it all back. So the diaphragm is typically ply on top of the existing timber, and it's solidly connected to all the internal walls. First floor, same story really. We had to make those diaphragms work. The floors are unusual sizes, and they were sort of having to look after themselves in the local areas. So the walls themselves had to be particularly joined to the diaphragms. And same again for the roof. You can see that there's a combination of the diaphragm in the roof of structural steel, where there's a big gap, and there's also that at the top level through the roof areas, lots of ply as well. Extremely complicated. And you see the roof form there had traditional old trusses, and the ceiling was built up following that truss. So the detailing around the connection to the walls, forming a diaphragm across through there, meant the whole lot of structural steel had to be installed in those different levels and bracing all the way through. The asbestos was removed out of the top areas before we could move into this. There was a large scale asbestos issue that had to be resolved prior. But instituting that structural steel within those spaces was incredibly complicated and time consuming. Next part of it was, once you've got your diaphragms going, you have to check all the walls. So this is a while ago now, and this was before our guidelines had come out, but we had talked quite closely with Professor Ingram in Auckland Uni about sort of what are the best ways of doing this. So this is a bit of a combination of assessment through the new Red Book guidelines, and also some of the methodologies that were being developed at Auckland University. So the walls were found to be typically quite strong and longitudinal in plane, but often quite weak out of plane when you've got a face load that's happening onto these walls. So and remembering that we couldn't actually touch the outside, so all of the strengthening was on the inside. So that was with a carbon fibre type system through Typo, and all of the external walls with the cavity all had to be stitched together. So it's pretty traditional engineering, but it was quite time consuming actually going through stitching those walls together, installing and embedding, cutting and chasing into the fibre where it was needed, and just on top for other parts. Bearing in mind that we had to recreate the original courts as they were originally. And if you think, we're having to get a good bond, we're onto bare masonry or block, and we had to actually get a really good bond, and then you had to remember that, yes, we've got to go back again in the future. So it was quite a challenge to understand for the architect that, this is engineering, because the brief was, it's engineering first. We need our 70%. The architects have to do as well as they can within the provisos of that brief. So it was a bit of a back to front brief from the last presentation. And just a typical sort of bit of the complexities of the wall strengthening. There's the fibre in there, 2 layers, single layers. We've got additional strips where we've got openings, and we're joining existing walls to the fibre as well. So we elevated every wall on the whole job, and to portray the actual strengthening that actually went into that. The tower strengthening was a challenge all by itself. You can see on your left that we've got some structural steel angles, which on a masonry wall were really not going to be doing anything. So they came out. This was a different scenario because it was so tall and so heavy. This became a reinforced concrete solution. So we had a shotcrete type solution, and we popped in concrete slabs with some very lightweight timber floor systems from stair to stair to stair. So that came out to minimise the actual span of the concrete walls. And that was a sort of challenge in itself to be able to actually get in there, spray concrete, put concrete in. And we had a few steps and a few changes of thicknesses on the way through as well. So we had some changes of concrete where they addressed the actual change in thicknesses of the masonry as it went higher, as we got top. Always the outside was all remained level, but the inside tiered inwards. The mentioning before that we needed a very large raft foundation, and the foundation itself had to be supported by improved ground. So we had specialist geotechnical engineering into that ground with jet piles to improve it quite a long way down till we got to effectively a bedrock. And then we built with underneath the tower, and it was a piece by piece replacement of the concrete slabs there, and replaced with all of the concrete raft underneath. So that was also extremely challenging to get that underway. The usual sorts of details that we get, sort of plywood to walls and all sorts of funny details. Don't need to dwell on those if everyone's really keen. I've got all the drawings. But yes, fundamental to the connectivity of the building. So the Tourells I mentioned before, these were sort of offset, beautiful carvings, but they were actually stacks of stone put one on top of the other. How they've still stayed there all these years, it's quite surprising. So these had to be individually strengthened with rods drilled and grouted, and then covered up afterwards, and then backstayed back to the structure behind them. So these were very, very heavy. Surprising they'd never actually come off in a minor shake, because there was really nothing holding them there at all. So it was a big deal for Dunedin when it was finally finished, 2018, I think it was a while ago now. The whole of Dunedin and all of the law courts, high judges, Prime Minister came down, and we had a very ceremonial opening, a march. All of the powers that be in the legal world were there just to celebrate getting back their building again. It had originally just the little bits of offices at the very end outside of the fall zone. And now they've got the whole building back and recreated to a level. And I don't have too many photos, but that was the level of before and after. Absolutely stunning bit of architecture on the inside, beautiful timber work. And the architects and the heritage architects did a wonderful job managing to conserve that, taking it all away, taken away and carefully stored and carefully numbered, brought back all in the right place, and recreated again to a fantastic level, really. You might notice the inside. This is where the stair is. The prisoners pop up in front of the High Court judges there without having to walk through the courts. They're brought in from the jail next door. Just a few acknowledgements. Ministry of Justice, they were doing a nationwide upgrade of the heritage, and they were happy to just really devote that large amount of money that this took to get this both to a seismically high level, but also to recreate the history that has been there since 1902. So other parts, because it's always a team approach to these things, we've got RDT Pacific, Stevenson and Turner, Ian Bowman on the heritage architecture side, GSL, PHC, and full credit to the amalgamated builders, because it really was a hugely challenging project, and they hardly ever grumbled, and they did a wonderful job. Thank you.
Thank you, John. What a beautiful building and really iconic. Yeah, thank you for that. So last presentation and two final speakers this evening, Greg McFetridge and Eoin Norton. Now, Owen's online. You guys got that sorted. Sorry, just looking to the back of the room. So I'm going to introduce Greg, and Greg has offered to introduce Eoin. So Greg is a general manager of operations at Naylor Love, a chartered professional engineer of 35 years of experience in the construction industry. Greg will share his work on the complex seismic retrofit project of the Wellington Town Hall. So thank you.
Thanks. Hi everybody. So as you heard, I'm Greg McFetridge, and you will meet Eoin Norton shortly. He can't be here with us today because he does have COVID. So we're both from Naylor Love. We're both engineers with Naylor Love, and we're going to run through a bit of a case study of what I think is currently the most interesting project, certainly in Wellington, probably in New Zealand at the moment, and that's the seismic upgrade and heritage refurbishment of the Wellington Town Hall. So we're Naylor Love. Our role on the project is as contractors, and I was part of the early procurement stages of the project, so I helped put together all the methodologies that got us the tender, and now Eoin has managed to pick up that on site, and he's the site engineer correcting all my mistakes and doing all the really hard yards. So I'll talk about some general stuff, and then Eoin will talk about the interesting stuff for engineers. So a bit of background to the building and to the start of the project. For those of you that do or don't know Wellington, the town hall is in the red square there in the middle of the civic precinct, right in the downtown of Wellington. It's a big brick building built in the early 1900s. on reclaimed land in Wellington, and it was originally built as the town hall and the whole civic administration and mayoral chambers. So as you can see, it was a really, really grand building. I say was. So a couple of floor plans there. Between Owen and I, we'll talk about a couple of the main features. So we have the West Hall and the Auditorium, which is a biggie, and then the East Wing is everything that you see, the Isla Theatre, the Merrill Suite, and the bit in the middle, which has got the grand stairs. And just like John, we have also got access to the old drawings, which are really cool and pretty useful. So the Wellington Town Hall has covered a lot of stuff in Wellington. It was well used up until 2013, everything from classical concerts and choir stalls, and you see the famous Beatles concert in the town hall. Right, as with most buildings of this age and nature, how it started isn't how it is now, and you can see that a lot of its decoration was removed. So what was once a really grand old lady isn't quite so grand anymore. A lot of that was taken off in the 1940s and earlier after a couple of earthquake events. And so we're left basically with what's there in 1975. The auditorium inside is really famous for its acoustics, and that's sort of a key part of the heritage refurbishment, is don't affect the acoustics, whatever you do. And the whole interior of that will remain very much as it was. So the project in 2013, the building was closed to the public. It was listed as being earthquake prone. A whole project was run through. That scheme never made it to construction, but it has come about as this other version. And so now we're in a really great position to give the building at least another 100 years of really good service. So on the heritage elements, obviously the whole exterior facade needs to be retained, and exactly as John said, it's pretty much a do not touch thing. We can make it better, but no different, and certainly no worse. Internally, a selection of pictures here. You can see the ceiling in the auditorium. So the auditorium is a pretty grand space. We've got some of the heritage plasterwork and the organ, which was removed in the 2013, prior to the 2013 project. And if you're really good at jigsaw puzzles, I'm sure the Southern Organ Company would welcome some help when it comes. So where the organ is, and you would have seen in the black and white photos, the choir stalls is another big bit of heritage fabric that needs to be retained or needs to be reinstated. One of the other big moves in the building is the main entry stairs, and they're quite a feature of the building, the mosaic floor and the stairs and the balustrades and everything else there. So they were a very important part of the project, and I say were in terms of heritage fabric, because you'll see some other photos that mean they don't look quite like they do now. The other heritage area is this, which is the Isla Theatre, which was the original debating chamber for the town hall, for the council meetings. And you can see there, this is well and truly under construction, with large parts of stuff taken out so we can do the engineering works prior to the heritage reinstatement. So talking about heritage fabric management, so with all these projects, you work very closely with the heritage architect and establish what stays, what goes, what gets taken away for refurbishment. And again, here's the choir stalls on the left, up towards the stage area, and the smaller photo there is a shot, and you can see the barcoding tags. That's not very clear on there, is it? Barcoding tags and individual numbers on each piece of timber that was taken out. So they've all been taken away here to a storage facility where the heritage architect will review it. Again, conserve what's to be conserved, what comes back. It certainly wasn't a demolition scope of work. It was a very careful dismantle for most of this work. If you do have time, go to the Naylor Love LinkedIn page. There's a really neat 5-minute video on the heritage elements of this. It's well worth a look. Spend your 5 minutes. It is worth having a look at. So where fabric needed to be removed, and sometimes it did, and we come back to the famous stairs, we did an awful lot of scanning and 3D imaging and 3D recording to give us both the quality of stuff that needs to go back, and also location, so that we can completely replicate what's there where it had to come out. Which is certainly from my point of view, having worked on a few of these projects, it's the first time we've used BIM and digital recording to the scale, and it's proved to be a real game changer. So well worth getting involved in. Before I hand over to Owen, I'll just run you through that's the heritage sort of element. So I'll run you through the project scope. Here's a section through the building. A long section, you'll see the roof trusses at the top, as sort of echo John's statement, that gets a new diaphragm built into that, as well as upgrades to today's acoustic requirements. This is a section through the auditorium, so you can see so that the space that's there, and what you will see in the middle is a basement space, which I'll talk about later. The main engineering works are in the basement space. It is a refounding and an installation of base isolators in a 100-year-old brick building, which really, when you say it quickly, sounds pretty easy, but it's really not. It has been described as knitting a jumper while you're wearing it, because it really is take something out, replace it, and move on. But you can see here, we've got 450 screw piles installed under the building. Inside a building, that takes some doing, and over 150 base isolators and sliding bearings, which are the small squares you see. And then in the middle, we have the other big move for the building. So once we've finished the sort of bluey purple coloured foundations and get the old building essentially back on base isolators, so it's refounded, won't settle, is pretty strong. The next big move is to create a 3 metre deep basement, which also happens to be 3 metres below the tide level in central Wellington inside a building. So it's a pretty big deal. And at the same time we're doing that, all the upgrade and re-strengthening works to the other spaces in the east wing will be carried out. Last slide from me. This is a sort of the before and after that shows the scope of what we're doing. So on the left, you'll see the big, heavy, unreinforced masonry wall with some stone facing on the outside. And then on the right, you will see what we are finished up with. So we've cut holes in the wall to install the upper ground floor beams. We've cast an 800mm thick raft on top of the existing basement floor, and we've installed isolators. And this is pretty much the state of the building right now. We continue with that until the isolators are all loaded, and then we can start with the basement works before we start on cutting the seismic gap. So this is where we magically hand over to Owen, and he's going to talk about the other engineering bits.
Oh, thanks, Greg, and good evening to everyone. Just getting back to my starting point here. I'm going to run through some of the specific engineering and temporary works challenges that we experienced and continue to face on this project. As Greg noted above, one of the key elements of this seismic retrofit involves refounding the piles both vertically and laterally onto a network of over 450 screw piles spread across the building. Nair Love were heavily involved in the design of the screw piles, and we worked closely with our piling contractor to find a suitable pile that could support the required loads whilst also taking the unique ground conditions beneath the town hall into account. One of the earliest engineering challenges we faced was to find suitable locations to complete the compression load tests. This testing required a rigid steel frame, which is the blue steel frame shown on the photo on the left-hand side. This test frame has a screw pile in the center and 4 perimeter screw piles, which act as reaction piles. Some of the tests were completed around the perimeter of the town hall, which were squeezed between the existing services down MFC Lane and Wakefield Street, and others were complete within the more open areas of the town hall, such as the Isla Theatre, which is shown on the right-hand side. Both completion of the screw pile tests and installation of the permanent work screw piles required considerable planning. Firstly, to ensure that we could access each pile, and secondly, to make sure that we didn't trap the machinery behind any completed areas of works. We used BIM to model the routes of the machinery through the town hall and identify difficult spots where the piling was obstructed. The photo on the left-hand side was used to prove that we could fit the machinery down the narrow southern corridor. Using BIM, we were able to identify that the main foyer stairs would need to be demolished to install the screw piles shown in red. It was originally intended by the consultants that these stairs would remain in place throughout the construction. Unfortunately, with the stairs in place, there would not have been sufficient access or headroom for installation of the piles. We worked closely with the client and architect in advance of any demolition to protect and salvage any heritage fabric. These photos show you some of the type positions that the piling machinery worked in, especially in the area of the main foyer. The 25-ton excavator shown has a modified weighted boom that created additional downward force during the screw pile installation, and then that reduced the size of the machinery that was required to get around the town hall. In some instances, the machinery only had 50 millimeters clearance either side to operate within. It should be further appreciated that each screw pile required 3 pieces of machinery for its installation: 1 to pre-auger the ground, 1 to hold the pile in place, and 1 to screw the pile to the required depth. Piles were generally installed in 3-meter heights and welded together as they were screwed into the ground. For external areas, we were able to use larger machineries for installation of the screw piles. To allow for the machinery and gear to reach their destinations, we had to develop access routes through the town hall. This required creating openings through the 700 millimeter thick URM walls. One opening was created at the southwest corner of the site with access from Wakefield Street. And another opening was created at the northeast section of the auditorium, which is the opening shown on the left-hand side. Once again, we worked closely with the client and architect to reduce the impact on the heritage fabric of the building. The openings were 4 meters wide, and the photo on the right-hand side shows the scale of the machinery that we were able to drive through the openings. Along with access, extensive temporary works was and still is required to allow for construction of the permanent works. The whole length of the auditorium was covered with a shrink wrap roof to allow for recladding works. Also, following discovery of rot at the auditorium truss ends, extensive propping was installed throughout the auditorium to support the trusses during the construction works. The photos here show the scale of the propping through the auditorium to support the trusses above during the construction. The propping in the auditorium was also designed to maintain the access routes in and around the building. At multiple locations around the town hall, existing diaphragms had to be removed to allow for construction of the permanent works. Temporary lateral propping was then required to provide out-of-plane restraint to the existing URM walls. The photo on the left shows lateral propping installed along the length of the West Hall following demolition of the existing structure. The props support the western side of the URM wall and are fixed into the neighbouring MOB building as agreed with the structural engineer. The photo on the right shows a unique truss propping configuration required to support the northern URM wall whilst maintaining access for construction. As part of the permanent works design, each URM pier location is to be refounded onto a new concrete ground beam, which cantilevers out over a base isolator. The picture on the left shows the layout of the URM piers along the northern elevation. This is the Civic Square side of the building. The detail on the right shows the proposed foundation arrangement for the URM piers. Note that the isolation plane will be formed just below the level of the ground beams. To allow for installation of the ground beam, vertical UC props were required to support the loads above. These UC props were then cast in place with the ground beams. These props were installed sequentially during the breakout of the URM piers and were situated to best avoid the reinforcement within the ground beams. The photo on the bottom right shows the piers with the permanent works ground beams complete. Following loading of the base isolators, the remaining brick portion beneath the ground beams will be broken out. Similar to the exterior brick walls, vertical UC propping was also required beneath the interior walls to allow for construction of the new foundation structure. We worked closely with the client and structural engineer to best determine the staging of the foundation construction so that at all times the Wellington Town Hall had suitable remaining lateral capacity. The photo on the right shows an interior URM wall in the old Isla Theatre following installation of the screw piles and completion of the temporary works. The area is then ready for construction of the concrete raft slab, with reinforcement being placed in the photo on the right-hand side. In some areas, unique temporary work configurations were required to support the large loads, while the base of the existing structure was demolished in preparation for the new foundations. The photos on the right-hand side are the circular columns of the main foyer shown in the slides earlier. One of the most interesting pieces of temporary works for the town hall involves propping of the external colonnade. The proposed strengthening works created some significant challenges, and as we needed to disconnect the base of the columns to construct the new foundations, but there is no obvious solution to support the weight of the 12-meter high columns while this work was underway. The permanent works required the entire area beneath each column, and so propping directly below was not possible. After exploring a number of solutions, it was decided to utilize a temporary steel truss to support the URM columns. The steel truss was supported by 6 UC columns, which were founded on top of the new screw piles. In other areas, the required temporary works clashed with the proposed base isolators, and so templates were utilized to fix the location of the base isolators during construction. This presentation outlines some of the interesting works and challenges that the Wellington Town Hall team have encountered, and we thank you for listening.
We'll wrap it up here. We aren't answering any questions online. Thank you so much for attending, and we hope you enjoy the rest of your night. See ya.